properties of equipotential surfaces. The potential of a equipotential surface has a single value, and because of that, distinct equipotential surfaces cannot intersect. So let us say this happens to be an equipotential surface. This surface will have some value of potential. Let's say V is equal to 5 volts. V1 is equal to 5 volts, let's say. If we have got another equipotential surface here, then let's say this surface has V2 is equal to 10 volts. We can conceptually visualize that this surface can never even touch this surface. They cannot intersect even in one single point, let alone a line or a surface area. Why? Because all the points on this equipotential surface have the potential V2 is equal to 10 volts. All the points are going to have the potential V2 as 10 volts. Here on this equipotential surface, all the points are going to have the potential 5 volts. V1 is equal to 5 volts. So what does this imply? If they intersect and if they have one point in common that belongs to both the surfaces 1 and 2, then in that case there would be a confusion. What would be the potential of that point? Will it be 5 volts or will it be 10 volts? This confusion is not allowed. That's why equipotential surfaces do not intersect. They cannot intersect. And every point on a given equipotential surface has a single value of potential. Electric field lines are perpendicular to equipotential surfaces. So let us say we have a surface over here like this, and let us say we are to draw electric field lines. We would be able to see that electric field lines are going to be perpendicular to the equipotential surface. Why is this so? Because if the electric field were to hypothetically have a component along the surface or along the tangent to a surface, we could detect a potential gradient or a potential change there, because we know that dV is equal to minus E dot dl. So if electric field has a tangential component, then in that case along the equipotential surface we will have two points that will have different potentials, but that is not allowed. All the points on the equipotential surface are supposed to have the same potential. So because of that, the electric field has to necessarily be perpendicular to the equipotential surface. Work done to move a point charge from one position on an equipotential surface to another position is 0. So let us again visualize this particular aspect. Let us say this is an equipotential surface, and let us say here we have a point charge. Now if this point charge is moved, let's say it's at location A, and let's say if we move this at location B, even if we move it along the surface or we take it out of the surface and bring it back onto the surface, then the work done in moving this point charge from A to B is going to be 0, because work done will correspond to change in the potential energy, or rather the potential of this particular associated with this particular charge. So work done is equal to negative change in potential energy. We know that the change in potential energy is going to be 0, so work done is also obviously going to be 0, because both the points A and B belong to the same equipotential surface. The surface of a conductor happens to be an equipotential surface. So if we have a conductor, then in this particular scenario, if this is a surface of a conductor, it happens to be an equipotential surface, and naturally it follows that electric field lines are going to be perpendicular to the surface of a conductor in electrostatic situations. So surface of a conductor is an equipotential surface. For point charges, equipotential surfaces are a concentric sphere. So here we can see that there is a point charge Q. Here this is very easy to prove, and let's in fact go ahead and do that. We can see that we can write down the expression for V of a point charge. It is 1 upon 4 pi epsilon naught Q divided by R. That is the expression for V. This is R, the distance from the center to the radius. This is the distance R, and we can see that if we put this as constant, we have got everything else is constant, therefore we'll get R equal to constant. And when we have this situation that R is equal to constant, what do we have? Clearly and naturally we'll have a sphere of a given radius will have a certain value of the potential V. If we have another sphere of certain other radius, then it will have a different value V2. If we have a third sphere of some other radius R3, then it will have a different value V3, so on and so forth. So equipotential surfaces are essentially concentric spheres. So this is what we have to note over here. For an infinite line of charge, equipotential surfaces are concentric cylinders. So let us say if we have an infinite line of charge, let's say this is our infinite line of charge, then in this case, for this infinite line of charge, we are going to have concentric cylinders as the equipotential surfaces, and one such cylinder we have represented over here. This is the cylinder. This is like one equipotential surface, another can be like this, another can be like this, and so on. Different cylinders will have different value of the potential V, and electric field lines are naturally going to be perpendicular to these equipotential surfaces. So this is a situation wherein we have cylindrical symmetry. Here, this is a situation wherein we have spherical symmetry. And then this third situation is a situation where we have planar symmetry. So let us say electric field lines are moving from left to right. These are electric field lines. These are moving from left to right. And equipotential surfaces in this particular scenario are actually these surfaces represented here as a cross section. But these planar surfaces that are parallel to each other and perpendicular to the electric field lines, these surfaces are the equipotential surfaces in this particular scenario, these surfaces over here. And naturally the electric field lines we can see are perpendicular to these equipotential surfaces. That is clearly and easily readily seen. For a dipole, so what is a dipole? We have got a plus charge and we have got a minus charge. So for the dipole, the electric field lines are as shown over here that we are highlighting as of now, and equipotential surfaces are these surfaces like so, and later they engulf the positive and negative charge like this after a while. So this is how the equipotential surfaces of the dipole are represented.